Welcome to this explainer. It turns out gravity isn't just some simple, boring downward pull. When you look at the precise paths objects actually take through space, gravity reveals itself as a highly intricate, shape-shifting geometric grid. Today, we're going to explore a famous mathematical coincidence regarding how things fall, why the messy real world absolutely shatters that coincidence, and how a really fascinating framework called base-scale calculus helps us map the unseen universe. Let's get right into it.
So to get us started, I want you to imagine tunneling straight through the Earth. We're investigating a classic physics puzzle here. If you drop an object, is the exact path that builds the most speed identically the same as the path that perfectly balances gravitational forces to ensure equal travel times? Just think about that for a second. Are the absolute fastest path and the equal time path always the exact same curve?
Well, to answer that, we first have to define two incredibly demanding curves. On one hand, we have the brachistochrone. That's the path of fastest descent. This curve cares about one thing and one thing only: maximizing kinetic energy early on. It's going to dive steeply right at the beginning to build up high speed fast, even if it means taking a slightly longer overall route. On the other hand, we have the totochrone, the equal time path. This one is all about perfectly balancing restoring forces. Whether you drop a marble from the very top of the track or somewhere near the bottom, it'll reach the end in the exact same amount of time. Now, these two famous curves optimize entirely different things, yet on a flat plane under perfectly uniform gravity, they mysteriously merge into the exact same shape, a beautifully elegant curve known as a cycloid. Crazy, right? How is that even possible? Section 1. Inside the spherical cow, our perfect uniform planet. Let's see how this math plays out when we take a theoretical gravity train through the center of a perfectly uniform, idealized planet. Notice how the shape of the curve depends entirely on the background field. On a flat plane with constant gravity, we get the cycloid, which is basically traced by a point on a circle rolling along a flat ceiling. But if we go inside our idealized, uniform density planet, as we burrow toward the core, gravity decreases linearly. Here, the curve becomes a hypocycloid. You can kind of visualize that as a smaller circle rolling inside a larger one. Or, if we were operating above the planet's surface in an inverse square gravity field, we'd get an epicycloid, curving along the outside of a sphere.
Let's zoom in on that middle scenario, falling inside our perfectly uniform planet. Why on Earth do the fastest path and the equal time path stay identical here? It's because the background physics of our spherical cow naturally acts as a simple harmonic oscillator. It literally obeys Hooke's law. This means the restoring force along the curve is exactly proportional to the distance left to travel. Thanks to this beautifully natural physical harmony, the brachistochrone and totochrone stay perfectly matched as a single elegant hypercycloid tunnel.
Section 2. Reality breaks it, and the coincidence is shattered. So what happens when we leave the pristine, idealized math behind and introduce the messy reality of planetary geophysics?
Spoiler alert, the universe is rarely a perfectly uniform sphere. Real planets actually look a lot more like a Pareto distribution. Think of it as the 80-20 rule applied to planetary mass. In reality, mass is overwhelmingly concentrated in a hyperdense iron core, with a long, fluffy tail of lighter crust and mantle stretching outward. Because you bypass very little mass as you dig through those outer layers, gravity doesn't just decrease linearly. Instead, as you approach that incredibly heavy core, gravity violently spikes, peaking right at the core boundary before finally dropping to zero at the absolute center.
And because of this intense power loss spike at the core, our beautiful mathematical coincidence is absolutely shattered. The harmonic oscillator environment is just completely destroyed. So, the two curves have to adapt to this extreme gravity well in totally opposite ways. The brachistochrone, our fastest track, warps into this massive steep plunge. It basically has to sacrifice horizontal distance to steal maximum velocity from that hyperdense core as early as possible. Meanwhile, the totochrone, our equal time track, has to do the exact opposite. Because gravity scales up so aggressively, an object dropped from up high would accelerate way too fast. So the curve flattens out near the core to artificially damp the object's speed. That single hypocycloid we saw earlier, it literally splits into two distinct non-standard shapes.
Section 3. Shifting base scale and mapping the breakdown. To understand exactly why the math breaks down at the core and how we can actually map it, we have to transition to the framework of base scale calculus.
See, traditional point-and-line calculus actually struggles pretty hard with these extreme power law environments, which is exactly where this specific discrete math comes in. Base scale calculus introduces an absolutely crucial concept, the log base d. Think of this simply as a localized gravity profile. It's a discrete decay or compression rate between 0 and 1 that governs how the geometry itself scales. By introducing log base d, we can mathematically model how this physical breakdown happens dynamically across a warped, shifting geometric grid. It literally dictates the changing rules of the space itself.
So, the major takeaway here is that moving from a uniform planet to a compressed core changes base d from a flat constant to a shifting variable. In our uniform spherical Cal field, the scaling factor doesn't shift at all. The rules of the geometry remain completely invariant, which is what allows one single curve to solve both the speed and time optimization problems perfectly. But in a Pareto field, our messy real-world planet, base d becomes a localized variable. As the object falls through different zones of density, the track must constantly change its geometric scaling rule, the background geometry itself is morphing, and that is exactly what forces our two curves to diverge.
Now, there's another major problem with a hyperdense core. Classical calculus tends to break down at the center of a power law mass profile by falling into an infinite point singularity. Yanks, right? But instead of falling into an infinite mathematical black hole at the planet's center, base-scale calculus anchors everything using a fascinating concept called the quark. The quark provides a fixed, discrete physical boundary, which we label d0 equals 1, that totally replaces the zero-dimensional ghost point. This perfectly resolves the paradox and gives us a discrete, countable, and stable surface right at the heart of the intense gravity well.
But guys, here's where it gets truly mind-bending. This divergence of curves, it only applies to massive objects. Massive falling objects get dragged and warped by these shifting decay rates. We call this the square limit of mass mechanics, because they rely on changing velocity and area packing. Photons, however, play by completely different rules. Photons exist in the line limit. Because their quantum velocity is permanently locked at the speed of light, c, they don't fluctuate to adapt to a geometric curve. They suffer zero lattice decay. That means they bypass this power law trap and its asymmetric drag completely. The math that dictates the paths of heavy planets and falling marbles simply does not constrain light in the same way. Mind blown, right?
And this brings us to a really beautiful synthesis. As perfectly stated in our source material, whether you are tracking a marble on a track, a seismic wave through rock, or light through a galaxy, the curve tells you the field, and the field tells you the mass. This brilliantly illustrates why these geometric breakdowns matter so much to astrophysicists. By understanding exactly how and why paths diverge, like how a base D shift shatters our perfect hypochloroids, we can literally map invisible density in even dark matter halos, simply by reverse engineering the geometry of the curves we observe out there in space.
So, the next time you drop an object and watch it fall, remember that it is actively negotiating an incredibly complex, shifting geometric grid. It really leaves us wondering, if analyzing the warped path of a falling object can map a planet's hidden iron core, exactly how much of our unseen reality, the dark matter, the hidden structures of the cosmos, can be mapped just by analyzing the curve of a falling star or the trajectory of light? It's a profound thought to leave you with today. Thanks so much for joining me on this explainer, and keep questioning the shape of the world around you.